Pure quantum computers can't solve most real-world problems yet. Too much noise, too few qubits. But hybrid systems, where classical computers and quantum processors work together, are running drug discovery experiments at Pfizer right now. This is what quantum classical hybrid computing actually looks like in 2026. Welcome to AmTalk Soft. I'm going to show you exactly how hybrid quantum classical computing works, the architecture, the algorithms, and the real applications running today. Here's the core problem. Quantum computers are incredibly powerful in theory, but in practice, today's quantum processors are fragile. They make errors. They lose their quantum state in microseconds. We only have a few hundred to a few thousand usable qubits. Pure quantum algorithms like Shor's factoring algorithm need millions of error-corrected qubits. We're not there yet. So what do you do with the noisy, small-scale quantum hardware we actually have? You use it strategically for the parts of a problem where quantum gives you an advantage, and you let classical computers handle everything else. That's hybrid quantum classical computing, and it's how quantum is actually being used right now. To understand why hybrid exists, you need to understand what makes quantum computers hard. A qubit, unlike a classical bit, can exist in a superposition of 0 and 1 simultaneously. When you run a quantum algorithm, you manipulate these superpositions to encode the solution to a problem. The answer emerges when you measure, but there's a fundamental problem. Qubits are incredibly sensitive to their environment. Any vibration, temperature fluctuation, or electromagnetic interference collapses the superposition before your computation finishes. This is called decoherence. Today's best quantum processors from IBM, Google, and IonQ have coherence times measured in microseconds to milliseconds. And even within that window, operations introduce errors. IBM's best processors have gate error rates around 1 to 2% per operation. Run a 1,000-gate circuit, and errors compound catastrophically. Quantum error correction can fix this, but it requires 1,000 to 10,000 physical qubits to produce one reliable logical qubit. IBM's 2026 roadmap targets 100,000 physical qubits for fault-tolerant computation. We're at around 4,000 today. So pure, fault-tolerant quantum computing is at least 5 to 10 years away. This is the NISQ era, noisy intermediate-scale quantum. The machines are real. The noise is real, and hybrid algorithms are specifically designed to work within these constraints. Hybrid quantum classical computing uses a specific pattern. The classical computer prepares a quantum circuit, the quantum processor executes it, the result comes back to the classical computer, which then adjusts the circuit parameters and runs it again. This loop is called a variational quantum classical optimization loop. The key insight is that you don't need a perfect quantum computation, you need many imperfect ones, combined with classical optimization, to find a good solution. The quantum processor handles the parts of the problem that benefit from quantum effects, superposition, entanglement, and interference. The classical computer handles everything that classical algorithms do well: optimization, data processing, and decision-making. Think of it like a coprocessor relationship. The GPU doesn't replace the CPU. It offloads specific computation types where it has an advantage. The quantum processor does the same thing, but for a completely different class of problems. The classical quantum interface works like this in practice. You define a parameterized quantum circuit, which is a circuit with adjustable rotation angles on the qubits. The classical optimizer, usually a gradient-free method like COBYLA or SBSA, searches the parameter space. Each iteration sends new parameters to the quantum hardware, which runs the circuit and measures the output. After dozens or hundreds of iterations, the system converges on a near-optimal solution. The most important hybrid algorithm today is the variational quantum eigensolver, or VQE. It was designed specifically for quantum chemistry, finding the lowest energy state of a molecule. Why does that matter? Because the lowest energy state of a molecule determines its chemical and physical properties. Simulating molecular energy on a classical computer requires exponentially more resources as the molecule gets larger. A 50-atom molecule can take thousands of years on classical hardware. VQE can potentially solve this in hours on quantum hardware. Here's how VQE works. You start with a parameterized quantum circuit called the ansatz. This is your guess at the structure of the molecule's quantum state. The circuit prepares that state on the quantum processor. You then measure the expected energy of that state using the quantum hardware. The classical optimizer takes that energy value and adjusts the ansatz parameters to reduce the energy. Repeat until you converge. The circuit depth is shallow enough to run on NISQ hardware. That's the key. You're not running a perfect quantum simulation. You're using quantum measurement to evaluate energy functions that are classically intractable to compute, while relying on the classical optimizer for the search. Pfizer and Merck are using VQE variants to simulate how drug molecules bind to protein targets. It's not ready for production drug discovery yet, but it's showing promise on problems that couldn't be approached classically at all. The second major hybrid algorithm is QAOA, the quantum approximate optimization algorithm. Where VQE targets chemistry simulations, QAOA targets combinatorial optimization problems. Combinatorial optimization is everywhere in industry. Portfolio optimization in finance, supply chain routing in logistics, network traffic scheduling in telecommunications. These are problems where you're searching through an exponentially large space of possible solutions, looking for the best one. Classically, these problems are NP-hard. For large instances, you use heuristics approximation algorithms that find good enough solutions in reasonable time. QAOA does the same thing, but uses quantum interference to search the solution space more efficiently. QAOA works by applying alternating layers of problem-specific and mixing quantum gates. More layers means higher approximation quality, but deeper circuits, more noise on real hardware. The classical optimizer tunes the angles on those layers. Today's QAOA implementations on real hardware show quantum advantage only for small instances. Researchers are still working on scaling it to problems where it clearly beats classical heuristics. But J.P. Morgan Chase and Goldman Sachs are already running QAOA experiments on portfolio optimization problems, betting that near-term hardware improvements will push it into practical territory. Let's ground this in what's actually happening today, not in 5 years. In pharmaceuticals, VQE-based molecular simulation is being used to study enzyme behavior and protein folding. Pfizer, AstraZeneca, and Roche all have quantum computing programs. The target isn't replacing classical simulation, it's tackling specific simulation problems where classical hardware runs out of memory or time. In finance, QAOA and quantum annealing are being applied to portfolio optimization, risk calculation, and options pricing. Goldman Sachs published a paper in 2023 showing quantum advantage in Monte Carlo simulations could be achievable at around 8,000 qubits. We're not there yet, but the math works out. In logistics, D-Wave's quantum annealers, which use a different paradigm but a similar hybrid approach, are being used by Volkswagen for traffic flow optimization and by DHL for delivery route planning. These are in production, not research. What these applications have in common, they involve optimization over a space too large for classical brute force, but small enough that today's noisy quantum hardware can contribute signal. The pattern for near-term quantum advantage is problems with a known classical hardness, modest qubit requirements, under 1,000 qubits, and tolerance for approximate solutions. That's a narrow window, but it's growing as hardware improves. The quantum hardware landscape in 2026 has three major players offering cloud access. IBM Quantum provides access via IBM Quantum Platform. Free tier gives you access to 7-qubit processors. Paid tiers give you time on their Heron and Condor systems with 127 to 433 qubits. The programming interface is Qiskit, which is Python-based and has excellent documentation. IBM's roadmap targets a 100,000 qubit error-corrected system by the early 2030s. Google's quantum hardware is available through Google Cloud Quantum AI. Sycamore demonstrated quantum supremacy in 2019 on a contrived problem. Their current focus is on error correction research rather than broad access. IonQ and Quantinuum use trap-tie technology, which achieves higher gate fidelity than superconducting qubits at the cost of slower gate speeds. IonQ is available through AWS Bracket and Azure Quantum. For developers, the easiest entry point is IBM Quantum Platform with Qiskit. You can run circuits on real quantum hardware for free within usage limits. PennyLane is another excellent library that works with all major hardware backends and is specifically designed for the variational hybrid algorithms we discussed. If you're a developer who wants to actually work with hybrid quantum classical systems, here's the practical path. Start with simulators, not real hardware. Qiskit and PennyLane's built-in simulators let you run quantum circuits classically, which is free, fast, and noise-free. This is how you learn the programming model. The programming model works like this. You define a quantum device, either a simulator or a real hardware backend. You write a quantum function using a circuit-building API, gates, measurements, observables. You wrap it in a classical optimization loop. PennyLane makes this almost identical to writing a neural network in PyTorch. You define the circuit, compute gradients via parameter shift rules, and update parameters with any classical optimizer. The quantum classical boundary is the critical design decision. Minimize quantum circuit depth. Every gate adds noise on real hardware. Maximize what the classical optimizer handles. Think of the quantum circuit as an expensive function call that you want to make as few times as possible. Here's what to take away from today. Fault-tolerant quantum computing needs millions of error-corrected qubits. We're 5 to 10 years away. Hybrid quantum classical systems work today, using NISQ hardware within its constraints. VQE and QAOA are the two dominant hybrid algorithms, one for quantum chemistry, one for combinatorial optimization. Real applications are running right now in pharma, finance, and logistics, not theoretical, but also not yet production scale for most problems. IBM Quantum and PennyLane are the easiest entry points for developers. The quantum classical boundary is the key design decision. Keep quantum circuits shallow, let classical optimizers do the heavy lifting. If you found this useful, subscribe. We publish new videos on AI, cloud, and software engineering every week. The next video covers edge AI, running models on Raspberry Pis, phones, and factory sensors, which connects directly to what we covered today on distributed compute. See you there.